All right, so I'm going to do a hypothesis test problem out again using this graphic organizer. So I'm not going to actually do this problem. I'm going to do the next problem, and you're going to do this problem. But I just wanted you to see that I'm going to do the same steps for the problem that I do. So I'm just going to kind of like keep this next to it. All right, so for my problem, it says a large insurance company claims that 80% of their customers are very satisfied with the service they receive. To test this claim, a group surveyed 100 customers and found that 73 are satisfied. Based on these findings, can we reject the claim that 80% of their customers are very satisfied? Okay, so the first thing that we're going to do is we're going to do our hypotheses. So I'm literally going to, I don't have the think, show, tell here, but I'm going to do the same steps. Okay, so the null hypothesis is always, for proportions, P equals something. And in this case, they're claiming that 80% are very satisfied. All right, and the alternative is it says, can we reject the claim that 80% are very satisfied? So we need to think about that and say, do we want to know if it's not equal to 80, less than 80, greater than 80? Well, technically, if it's, it leads you to kind of think that it would just be not equal to 80. However, if their sampled customers are more than 80% that are satisfied, the company's going to be happy with that. So really what we want to know is that less than 80? Because if it's less than 80, that's when the company's going to have a problem. Okay. Now for the model, we need to do the assumptions and conditions, which are the same as they were. So random. I believe it says it is an SRS. Independent would be no. Population is finite because you can count the number of customers. And a lot of you are saying just yes to independence. And anytime you can count your population, it's not yes. Okay, so a lot of you on your quiz or your quick check keep saying yes to this. Stop saying yes to this unless it's the population is not countable. That's the only time you can say yes. But we can say that 100 is less than 10% of all their customers because it's a large insurance company. So I'm assuming they have more than, 1,000 customers. All right, and then success fail. Now for success fail, we need to find 80% of 100 and then 20% of 100. Okay, remember, it's not just the 73. Okay, with a hypothesis test, it's all about this 0.8 here. So this is going to be 80 greater than or equal to 10, 20 greater than or equal to 10. Okay, so a lot of you are getting the random and you're getting this, but you're missing the 10%. You can't skip this. Okay, you can't skip it unless it's, if it truly is independent. The population is not finite. Okay, all right, so that's the assumptions and conditions. So our model is going to be a normal model with a mean of 0.8 and a standard deviation of 0.8 times 0.2 over 100. So this right here is our model, okay? This is model. Okay, so that's the model part of the show. And now the mechanics. We're going to do the mechanics. Okay, why does this phone keep going in and out? Sorry. There we go. The mechanics of the test where we calculate the z-score and the p-value. So my z-score is going to be my p-hat, which from the problem is 73 out of 100. So 0.73 minus 0.8 divided by, and I got to find out what that standard deviation is. So the square root 0.8 times 0.2 over 100 is 0.04. It's negative 1.75. And then my p-value is going to be NCDF. Since it's a less than, it's going to be negative infinity to negative 1.75, 0, and 1. You can also do negative infinity, 0.73, 0.8 and 0.04. Doesn't matter. Paste. And we get 0.04. Okay, so this is an interesting one because we have things that contradict each other. All right, normally if my z-score is within 2 standard deviations, I'm okay. But if my p-value is less than 0.05, I'm not. So we have contradicting things happening here. So this is why I'm going to tell you to start relying on the p-value, okay? Because in actual statistics that's used in the real world, the p-value is way more important than the actual test statistic, okay? So for my conclusion, which is my last part, I'm going to introduce something called an alpha. And I'm going to state that my alpha is 0.05 because that's the normal alpha level. And what this alpha level means is if your p-value is less than this number, we reject HO. Okay, so this is like your cutoff for what's considered to be unusual or statistically significant. And this can change. So in the real world, this number changes. So if you're a pharmaceutical company and you're testing something, you're going to want to make this very, very small, like 0.001, so that your results better be super, super, super unusual because you're dealing with a drug that people are going to take and potentially get better with. So you need to be really, really sure that your results work. Other companies that want to kind of use statistics to lie a little and make stuff work will give an alpha that's really high. They'll make an alpha of like 0.2. So all they need is the p-value to be less than 0.2, and they're like, yep, see, what we did worked. So you see how you can sort of use the alpha by changing this? You can use that to lie. And if you ever read a paper in college, which you will, of papers that have statistics in it, they'll always tell you what alpha they use and what their p-value was. Okay? So we're going to say we reject HO because my p-value, which is 0.04, is less than my alpha. Okay, so I have evidence. The true proportion of happy customers is less than 0.8. I don't know what it actually is. I just have evidence that says that it's less than 0.8. Okay, so from now on, when you do a conclusion with a hypothesis test, always look at the p-value, and unless I say otherwise, always use an alpha of 0.05. Okay?